Hello. In this video, I'll be going over AICE Physics Syllabus Code 9702, Paper 22 from February-March 2017. Question number 4 deals with the Doppler effect. State what is meant by the Doppler effect. The Doppler effect is when there is a shift in the observed frequency of a wave due to the relative motion between the observer and the source of the wave. So we'll say there is what is meant by the Doppler effect. The Doppler effect is an observed shift in the frequency of a wave due to the relative motion of the observer and the source of the wave. All right, the Doppler effect is an observed shift in the frequency of a wave due to the relative motion of the observer and the source of the wave. Part B reads, a child sits on a rotating horizontal platform in a playground. The child moves with a constant speed along a circular path as illustrated in figure 4.1. An observer is standing a long distance away from the child. During one particular revolution, the child, moving at a speed of 7.5 meters per second, starts blowing a whistle at point P and stops blowing it at point Q on the circular path. The whistle emits sound of frequency 950 hertz. The speed of sound in air is 330 meters per second. Determine the maximum frequency of the sound heard by the distant observer. Musicians, go ahead and comment down below what note is 950 hertz. And even if you're not a musician, go ahead and comment that down below. It's important here to note that Doppler effect questions, are oftentimes will be, pretty disruptive and annoying situations. Here, at least, the child is only blowing the whistle for half a revolution here. There's, you'll see examples of these where people are blaring car horns and, speakers and things like that. And so we just have to kind of say, well, we got to get some Doppler effect questions out of this thing. Determine the maximum frequency of the sound heard by the distant observer. Here you're going to use your table of equations which you are provided, which I have conveniently by. And so the Doppler effect equation is provided in the list of formula. And so that's the equation that's going to be helpful here. The maximum frequency heard by the observer is going to be the frequency observed, which will be equal to the frequency of the source times the velocity of the wave divided by the velocity of the wave. And because the child is speeding towards the distant observer at this point, that will be the point when the frequency will be maximum. When two objects are approaching each other, the wavelengths are going to be squashed together, and so that means they're going to be occurring more frequently, and so the frequency goes up, which means we need to subtract in the denominator here the velocity of the source. Now we're good to substitute in values here. So the frequency of the source is 950 hertz, which is a note. That's right, you looked it up or you knew it. Well done, well done. The velocity, 330 meters per second, divided by the speed of sound, 330 meters per second. And then remember, we're subtracting the 7.5 meters per second. That's the source itself is moving at 7.5 meters per second. So remember that the Doppler effect is because as this whistle is emitting waves, the child is moving, sort of catching up to the waves. And so as those waves are emitting, they're catching up to the waves that have already been put out, and so they're going to be observed as closer together or higher frequency. Typing that into the calculator, we've got 950 hertz times 330 meters per second divided by 330 minus 7.5 yields a frequency of 972 hertz, which you could, round to two significant digits 970 hertz. Describe the variation in the frequency of the sound heard by the distant observer. It's worth a quick calculation to see, what would be the sound heard as the child sort of moves away. This would be the minimum frequency heard, when objects are speeding away from each other. So 950 times 330, and this time we're going to divide by 330 plus 7.5, so 337.5, and that yields a minimum frequency of 929 hertz. So frequency minimum is going to be 929 hertz. The maximum frequency we've just calculated up here to be 972 hertz. So the frequency will vary between 972, and then it will go down at this point. The object is neither speeding towards nor away from the observer, but just sort of side to side. And so at this point in the child's motion, sort of halfway between points P and Q, P plus Q over 2, there will be observed at the same frequency that the child hears the whistle at, 950 hertz. And so it's going to go from 972 down to 950 at this point, and then keep decreasing to 929 hertz there. You would want to sort of put that into your own words and describe that variation in the frequency heard by the distant observer. The frequency decreases from 972 hertz to 929 hertz. All right, it says turn over here. Let's see if we got, I don't know if you can read that, pop. So pop, oh yeah, pop quiz. Good, you stuck around for the pop quiz. And it is to describe the Doppler effect. All right, this is AICE Physics, syllabus code 9702, paper 21, from May-June 2017. Pause the video, make sure you've got that paper handy, and go ahead and try to calculate the answer to this question. Once you've had an attempt at that, go ahead and replay the video and check your work. All right, hopefully you feel pretty confident about this calculation. It's very similar to the one that we just did, but you have to solve for a different variable there, right? And so hopefully you were able to work through that. Describe the Doppler effect. I'm not going to take the time to rewrite what we just had on the previous paper, but hopefully you had that handy there. And we'll move on to part B. A car travels with a constant velocity along a straight road. The car horn with a frequency of 400 hertz is sounded continuously. A stationary observer on the roadside hears the sound from the horn at a frequency of 360 hertz. The speed of sound is 340 meters per second. Determine the magnitude v and the direction of the velocity of the car relative to the observer. And so this question again illustrates my point about sort of, the examples that they give here. So this person is just blaring their car horn continuously, sounded continuously, the car horn. It's like, come on, is there some kind of an emergency here or what? Anyway, we'll go through the calculation. Remember that the Doppler effect tells us that the observed frequency is equal to the frequency of the source times the velocity of the wave divided by the velocity of the wave plus or minus the velocity of the source. Let's begin to extract the data from the question here and substitute in. We know that we're going to determine the velocity v of the car, so we're solving for the velocity of the source. The observed frequency is this one. An observer hears the sound of 360. So 360 hertz is the observed frequency. The car horn with a frequency of 400 hertz is sounded continuously. And so the frequency of the source, 400 hertz, and they tell us that the speed of sound is 340 meters per second. Divided by the velocity of sound, 340 meters per second. And here we can see that the frequency has decreased. The frequency will decrease when the objects are speeding away, and so that kind of gives us the answer that we need right here. They're moving away from each other. And in that situation, we're going to add in the denominator. So we're adding the velocity of the source here. So here is our mathematical equation that we need to isolate the velocity of the source and solve. If we multiply both sides by this term here in the denominator, that will yield 340 meters per second plus the velocity of the source times 360 hertz equal to 400 hertz times 340 meters per second. Dividing each side by 360 hertz, we'll have 340 meters per second plus the velocity of the source equal to 400 hertz times 340 meters per second divided by 360 hertz is 377.8. Here the units are meters per second. If we subtract 340 meters per second, that's 4 there, from both sides, we'll have solved that the velocity of the source is equal to 37.8 meters per second, which is pretty close to 38 meters per second. We can report our answer to 2 significant digits here. So for the American students viewing here, that is just about 85 miles per hour. So here is a person that's continuously blaring their car horn at a frequency of 400 hertz, driving down the road away from the observer at 85 miles per hour. Go ahead and score your pop quiz accordingly, and then record your marks out of the total 4 here. Thanks for watching.